My name is Richard. I work at HFT Consultancy. What I'd like to do today is talk about high frequency trading and high performance computing, or how high performance computing is used in HFT trading. And I'm going to give one specific use case, and this is to do with high frequency trading in the context of market making. Now, the first steps that we do is to analyze the data. So there's a lot of assumptions made when we model the microstructure, the limit order book, and we're looking for kind of linear price impact, and we're looking for kind of a mean reversion. So this tests here. So we'll load the data to start off with. We'll look at the mid price, micro price, etc., and then we'll look at the spreads. So this is kind of totally normal to do the analysis to start off with. We'll look at rho, which is the order flow imbalance, right? And then we'll do some kind of an analysis here, and we'll do a kind of rho transition matrix. So this matrix here is for 1 second. I think this one's for 10 seconds, and this one's for, I don't know, I think this one's like a few number of seconds. This one's 30 seconds, and this one here is 60 seconds. So what we can see is that not only is it mean reverting, rho, which is the order flow imbalance, is mean reverting in a short period of time. It's mean reverting over a longer period of time, which is 60 seconds as well. So this is kind of important. I'm going to go into a order flow. I'm going to go into a kind of dynamic programming equation where I'm looking at the Hamilton-Jacobi-Bellman equation, where we've used that to model the microstructure of the limit order book. So it's important before we do that we analyze the L2 data or L3 data to make sure that our assumptions for the model are correct. Hi. So now we're going to be looking at how we actually model the limit order book, and we've got the assets. Well, the mid price of the asset is given here, right? So there's one component. This component here is the long-term component, and this alpha here is the short-term component, which is stochastic and mean reverts to zero. So this is the process, and so this is the drift, and this is how we model the process, the mid price process. Okay, and we use the kind of Hamilton-Jacobi-Bellman equation. This is a non-linear partial differential equation, and it provides necessary and sufficient conditions for optimality of control with respect to a loss function. So its solution is the value function of the optimal control problem, which once known can be used to obtain the optimal control for taking the maximizer or minimizer of the Hamiltonian in the HGB equation. Okay. So once we've got the resulting dynamic programming equation here, bear in mind that this is non-linear, and here are all the optimal postings that we've got to work out. These are the optimal postings that the trader should make. So once we develop this, so let's say we develop this in Python, we put in all the parameters. So that alpha that we had, these are the short-term alpha parameters, okay, and these are important, and we again, using the analysis that we've just done, that would kind of feed into this, right? So we've got the time big T times that's 60 seconds. Now in a really liquid market, that could be anything to 5 seconds, right? And then we've got the POV, which is like the volume of the market. So here it's saying we're 20% of the percentage of volume, which is unrealistic. That means we're really big, right? and this is the number and quantity of trades, and this is kind of like running penalty. So this is our risk aversion, and this is the volatility. Okay, so all these kind of parameters here that we're inputting here, normally we'd be, suppose that we're on the Nasdaq and we're looking at a really liquid equity, like we're looking at Facebook, and we're that's very liquid, right? And we've got a fixed feed, and we're taking all the market data from the limit order book. What we'd do is we'd take like 5 second windows. Inside that 5 second window, and I'm going to show you this in just 1 second. Because we're acting as non-informed traders, we have to get all our trades done, and then our position have to be closed at the end of that time window, whatever it is. And I'm just saying for a liquid market, that could be up to 5 seconds. In that same time period, in parallel, we would be looking at the market data, and then we'd be updating to looking at the kind of parameters, the big T point of view, whether we need to adjust them, the volatility, all these things, we'd be looking at that to say, right, do we need to, because as we create a model, we've got our model here, we have to feed in the parameters every time period. So when we finish trading, we can then feed those new parameters into another model, etc., etc., etc. So that way it goes on. So, and this is all done in Python, but I'm going to tell you what's the issue with how they've done it here. So this will give us an optimal surface. So when we solve this, this gives us an optimal surface. So where we are in this three-dimensional space here at 0 to 60 seconds, inventory plus 20 to minus 20, and here's my short-term alpha, which is my trend. This is for the sell side and the buy side. So think of it as a submarine. And if you're below the surface, you've got to get up. If you're above the surface, you've got to get down. Right? And you can do that by controlling your inventory. And when this time big T finishes, we've got to solve another model, and we've got to get given another surface, and then repeat and repeat and repeat. So that's how we do HFT when we're and this is a really simple. This is like one of the most simple, because this is at the touch. We're not we're not placing the limit orders deep into the limit order book. We're not doing any in real life. These models would be a whole lot more sophisticated. So this is just really kind of conceptually, how does high performance computing get into this? And I'm going to get into it because when we're looking at solving this, so we'll use a Crank-Nicholson method to solve this, and so it's basically looking at this is how we solve it. It's like a stencil. So we first of all, this is a nonlinear partial differential equation. We transform it into a linear partial differential equation. Then we use Crank-Nicholson. Now this approach here is very slow because this approach uses recursion. So one of the things that we do is, and we're going to go through that in the rest of the video, is talk about how we can basically speed up stencils and how we can get them to work extremely quickly. So how can we get solve a linear partial differential equation very, very quickly? And we use CPUs to do that, and we're going to go into detail what kind of CPUs we're doing, what kind of instructions we do. But this is just kind of giving the kind of base of why we're doing this. Okay. Thank you. Basically give you an intro. So we've got vectorization here, and this is ensuring that all our loops are properly vectorized. So in other words, our loops are using the vector registers. Then we've got multi-threading. So this is ensuring that we're handling any race conditions that would occur.
And then we've got cluster computing and distributed computing as well. So those are three kind of main prongs which we're going to try and improve it. And the example we're going to look at is going to be a stencil example, which is highly relevant. So we kind of see here's a stencil, and so the same kind of thing, you know, we use stencils for a number of reasons. We can use them in machine learning for edge detection, or we can use them to solve partial differential equations. So they literally are. So when we look at the kind of relationship between, especially if we're looking over a period of time and we're looking at how the kind of performance of computers has improved, and we look at Moore's law, if we look at the frequency, that has kind of obeyed that law. But we look at it in mid 2000, it kind of plateaued because, you know, we got to this kind of point where we couldn't improve the frequency anymore. We couldn't cool down the processors anymore. We kind of reached a wall. But if you look at the number of transistors, that has kind of carried on that trend. So, you know, overclocking isn't the answer. Plus, we can look at pipelining, and you know, we can increase or we can superscale the execution. But again, we're going to kind of run into out of order execution and the memory wall issues. So we're limited by the data locality and the access pattern in our application. So there is an unbounded kind of growth opportunity, but it is not automatic. We really got to look for all the types of or ways of vectorizing our code. We've got to kind of think in the context of linear algebra. How are we going to rephrase this kind of problem into a linear algebra problem, and therefore get the vector registers to handle it, and then the threads and distributed computing, etc., etc. So parallelism is the path forward, and we've known that for a while. And there are many different approaches to doing that. I mean, we've got FPGAs, we've got GPUs, but what I'd really like to do for the moment and for this video is focus on CPUs, and specifically the Intel architecture. We're not going to talk about AMD because AMD have got small, or rather smaller, vector registers. Intel have, in general, well, have always got some of the Intel CPUs have got larger vector registers, and that's really what I'm kind of interested in. Okay, so here's you know, this is going back a few years. So you know, this Intel Xeon 5 processor, this has been discontinued in 2018, but it's still a fantastic processor. It's capable of 3 T-flops per second, and there's a 490 gigabytes per second bandwidth. So this is the scalar instructions, and these are the vector instructions. So from single instruction, multiple data, this is going to be a single instruction, multiple data. Okay. That means that with one instruction, with one clock cycle, we can add multiple numbers in the vector register in one go, depending on what the vector length is, as opposed to having to do them one at a time. So that's what we're really trying to avoid. So this is kind of going through future, what we're going to be talking about later, how we're going to handle the cache, how we're going to facilitate data reuse, and how we're going to optimize the RAM for streaming. So, well, depending on the use case. So our use case is the stencil. So we're going to stick with that for the moment. And then we're going to talk about the design patterns in the clusters, etc. And cluster in distributed computing. Okay, we can see from here that these are the vector registers for Intel, and we can see that they started off at 64-bit, and then they've gone to 128-bit, and then 256-bit, and now they're 512-bit. And we're looking at how to vectorize our code. A lot of the time, if you're to use a for loop and you're to use it like this, there's going to be automatic vectorization. There is explicit vectorization, but you'd need to look up the Intel intrinsic guide to work out what that is, and we're not really interested in that, so we're going to skip that. So let's talk about automatic vectorization. If we're going to use the Intel compiler, which is the Intel C++ compiler, which is the HPC compiler, and we're to put this little tag at the end, qopt report, we'll get a report, an autovec.opt report come out, and that will tell us, that will show us, yes, this loop has been vectorized. So that's a really kind of good thing to run, and you can then get an output, and then we can kind of look at that output, and we can see if we can see for ourselves if it's been vectorized. There are limitations to automatic vectorization. It only does the innermost loop. So if you've got nested loops, it will only do the innermost loop. There has to be a known number of iterations. There has to be no vector dependence, and the functions within that loop must be SIMD enabled. So the pragma directive that we will use in our code to ensure that we get automatic vectorization will be pragma OMP SIMD to override. If we want to target a specific process architecture, we can do that, or we can target multi-architecture dispatches as well. Okay, so that's what I'm talking about, is that we can, when we're compiling, we can put these specific tags in there, and that will compile our code. But if our code's already got the pragma directives in there, then it's now future-proof, because any future architecture that comes out, we can just target as so. We won't have to rewrite the code. Now, automatically vectorized loops may be complex. So we've got this loop here. This is a single loop, and this is the Newton's law of universal gravity. So it's kind of complex, but this is going to be automatically vectorized, which is great. Now, also, if we want to, go into this in more detail, if we want to have loops with SIMD enabled functions, and then we've got to look at failed vectorization due to compiler decisions. So sometimes you have to guide your compiler. So here we've got two nested loops here, and we're making sure that vectorization happens by putting this pragma OMP SIMD on the outer loop. So here are all the kind of vectorization directives, and this is just a really kind of fast. I'm just kind of flying through this. You can, all this information is publicly available, and I'll kind of put the links below to show you where you can kind of get access to everything. But the main thing I'm trying to get across is how we use high performance computing using a stencil, and there are other kind of ways of doing it as well. So for each stencil has to have its initial boundary conditions, and you can set up different borders, and that way you can use distributed computing more. But for this case, we're just going to start off with a vectorization. Here's a pragma OMP declare SIMD. So this is in a separate file, and then we've got pragma OMP SIMD. So this is an SIMD function. So, and the SIMD enabled functions can also be complex. Okay, so there's a lot of power here in this. So this is true vector dependence. So this thing here is impossible to vectorize. This because it's depending on the last value here. So this is the dependence on the previous element. There is no dependence on the previous element in this one, so this is safe to vectorize. And this is an edge case at the bottom. Okay. So in this example, we're using a stencil and we're using it for edge detection. Okay, here's your set stencil. Okay, and it will loop through every single pixel, and it will use all the different. It will this is a stencil it'll basically use. Okay, now this can also be used, as discussed in Crank-Nicholson partial differential equations, solving partial differential equations. So for vectorization, the first step is that in the innermost loop, put pragma OMP SIMD, and this ensures vectorization of your stencil code, and we can see we've gained a performance. So the original code had a performance of 2.3, I think, operations per second, ops per second, and we've increased that to 17. So let's now have a look how we're going to increase that to 90 now. So we've got a partitioning data set between threads and processes. This is the difference between threads and processes. I'll just quickly talk about it. We've got a process, we have to do message passing, and we want to get information from one thread to another, we'll have to use mutexes. Okay, so we're going to use the OpenMP. There are numerous kind of frameworks for using threads, but we're going to use the OpenMP. We're going to specifically use the implementation of OpenMP, and one of the reasons we're going to do that is anything we use is going to be the Intel version. So we're using an Intel C++ compiler here. We're also going to use the Intel OMP library. We're also going to use the Intel MPI library. So we can see that we're putting this kind of tag in here, QOpenMP, and then we're setting the number of threads to 5, and we're running the code. So this is all kind of command line stuff. Now, as we're running all these loops in parallel, we want to take care of any kind of race conditions. So one of the best ways of doing that is using a pragma OMP parallel and this pragma directive pragma OMP4. So that will take care of any race conditions. These are the kind of loops scheduling modes in OMP. We've got static, dynamic, and guided. And we'll just quickly go through. This is, we're going back to the same use case, which is a stencil multi-threading, and we want to go back to, okay, so here we put a pragma OMP parallel 4, and then we've got our pragma OMP SIMD from before. So those combinations of those two directives we've managed to, improve the performance up to 90 ops per second, which is excellent. Okay, so now we're going to talk about kind of memory management. And that's not where we get the real kind of gain, but one thing we have to be aware of is when we look at this, we can see that if we try and do a ratio between the number of flops we're processing per second versus the kind of memory access, if we get a ratio, this is a ratio of 43. So if that ratio is over 50, then we can say that our application is compute bound. We have a compute bound application. If it's less than 50, then we have a bandwidth bound application. So it's important to kind of, just on the back of an envelope, just do that quick calculation, work out what that ratio is, and figure out. You can also kind of use a roofline model, which is what, there's little tools that are available that allow us to kind of look at that. This is the kind of RAM streaming. This is DDR streaming. Here is the AVX512 register. And here's your arithmetic intensity along the bottom. And here's your performance along the side. So when looking at the memory hierarchy, there are kind of a number of different memories in the computer. There's the L1 cache, there's the L2 cache. If we look at the L1 cache, that generally takes 4 to 5 cycles. This is L2 taking 17 to 18. The second it goes to RAM, you're looking at 100 cycles. So it's really kind of best For this specific use case, because we're not dealing with a lot of information to keep everything in the L1 cache, but there may be instances where we're dealing with a lot of data and we've got to use the RAM. So then we'd have to use the streaming, the RAM streaming that we talked about earlier. So this is a two-way architecture which has, and this is, so I don't really talk about this architecture too much because everything, all of this, everything's now being changed as we're moving to a kind of system on a chip kind of design where the RAM and the memory, etc., is all getting closer and closer to the CPU. So this is kind of more historical than anything else. So I don't want to spend too much time focusing on this, but I want to talk about the main kind of what we can do to look at the caches. So I want to talk about locality in space and time. Okay, so this is locality in space, and this, a minimal block of data transferred between your memory and your cache is 65 bytes long in the Intel architecture, aligned on 64-byte boundaries in memory. With 8 double precision values, we have 16 single precision values. Okay. We choose the loop order to maintain unit stride memory access. Okay. And that's it. And so this is the top kind of, when we talk about locality in space, this is what we're talking about, unit stride memory access. So all this memory is kind of next to each other. It's not kind of disparate like it is in this. So if we're to look at this multiplication, we can tell by this matrix to matrix multiplication. If we kind of change the order in which the different rows and columns are multiplied, we'll get a better performance. If we look at an array of structures or a structure of arrays, so here this is an array of structures, and this is suboptimal. So when we're looking at a structure of arrays, this is optimal because this guarantees unit stride access, which is locality in space. Okay, so there's the principle. For best spatial locality, order loops to get unit stride. Okay. Now the other issue is locality in time, and when we talk about locality in space and time, I'm going to come back to these topics. Here we're talking to it in terms of Intel, but we could also be talking about it in terms of sparsity when we're talking about backpropagation and when we're trying to learn in machine learning and how we can get neuromorphic supremacy and through spike neural networks. And then we'll talk about photonics, and that's really the future of technology. That's where the future lies. So we can get neural networks or deep neural networks that can learn 1 billion times faster than we can, because our spikes take the order of milliseconds to run, while these photonic spikes take picoseconds. So what's that saying? Is that saying, well, that can learn, if we had a brain that used photonics, that will basically be able to learn 1 billion times quicker than we can, billions of times quicker than we can. So this is spatial. Forgive me for that kind of digression, but now we're going to look at locality in space. And what we're trying to achieve in locality in space is we're trying to increase our cache hits rates. So we can see on this first example here, our cache hit rate without tiling is 0. Okay, when we include tiling, our cache hit rate is 50%. So the yellow ones, we've got loads of yellow ones here, right? And that's great. These are the cache misses. These are the cache hits, and we've achieved that by going from this code. We've got 2 nested for loops, but we've now got 3 nested for loops, and we've used a tile. Okay. This is another methodology, but we haven't improved the performance. So what we're going to do now is look at our stencil code again, and this is what we're going to look at. We're using some kind of streaming. So we're streaming, but also we're looking at this new directive here, which is pragma vector non-temporal. So this is kind of taking care of the caching non-temporal. So this is optimizing our locality and time, and we can see that this has kind of really improved the the performance of it. Now we're going to go into the final part, which is the distributed computing part. Let's talk about this. So this basically is the MPI library. And we can use the MPI in combination with OpenMP. So OpenMP takes care of the threading, and MPI takes care of the distributed computing. So that would be the best kind of outcome. And this is a kind of way of passing messages. So how do we pass messages between the nodes in our cluster and the distributed computing? And there's certain design patterns to do that. So what you want to do is you want to avoid any kind of situation where you're going to have a race condition. So the really kind of basic pattern is to use point-to-point communication. That rank could be a number like 0, the receiver could be a number like 1. So, and we've got this MPI send, and we've got MPI receive, and we've got some messages here, etc., etc. So, well, that's great. There's numerous kind of different design patterns that you can have. You can have parallel patterns, you can have collective communication, you can have broadcast, this is MPI broadcasting to different nodes, you can have collective communication scatter, you can have collective communication gather, you have collective communication reduction. So these are some kind of examples here, and if you look at here, we've kind of put in MPI rank, MPI size, and as we're running the code, we've got to run it in MPI run. We're running it with 4 nodes here, and so this is our cluster, and we've basically got our stencil here, and we've got our image here, and then we're running it, and this is the code that we've added on top of the code that was there before, and this is allowing us to distribute the process over these nodes, and we get a massive, just using 4 nodes, we managed to massively increase the performance from 1100 to 3100. So this is absolutely fantastic example of how we can use, and this isn't, we're not talking about being a performance engineer, we're just talking about low-hanging fruits, and what we can do to improve the performance of our code, and there are numerous kind of valuable use cases where similar stuff can be done. So it's extremely powerful technologies to become aware of. Of course, there are GPUs, there are FPGAs, but we can see that these CPUs are very powerful, and there's many more use cases within finance that you can use. So I'm going to stop the video here, and the next video is going to be on neuromorphic computing.